So today we're going to talk about some of the vector rules when it comes to derivatives and things. Now, remember, limits are amazing creatures. We know that the limit of a sum is the sum of the limits, the limit of a scalar multiple, the scalar multiple of the limits, the limit of a product, the product of limits, limit of a quotient, quotient of the limits, and the most important, the limit of a composition is a composition of the limits. But only the sum and scalar multiples apply to derivatives and to integrals. Which of those, if any, apply to vectors? So we want to make sure we have this down. So if I consider vector u and vector v, let's say, are elements of Rn in general. This is true for any. So if I'm in 2 dimensions or 2,000 dimensions, it doesn't matter. I just have to be in the same dimension. Then if I want the derivative of u of t plus v of t, based on how we defined vector addition is the vector of the sum of the components. This is in fact du dt plus dv dt. And if I take the derivative of a scalar multiple of a vector, that is in fact the scalar multiple of the derivative. And all I have to do is put the numbers in to see that that works. These are the same properties that apply to derivatives and integrals from the limits. But is there the equivalent of a product rule? Well, there actually are 2 different versions, because there's the derivative of a dot product, there's the derivative of a cross product. And the thing is, you will take derivatives of dot products periodically in math. You're never going to take the derivative of a cross product. Even though there's a set of rules in the text, I'm not going to bother with them, because the next derivative of cross product that I take will be the first one I've ever actually taken. I can't even think of a scenario where that comes up. So I want to take the derivative of u of t dotted with v of t, very specifically. Well, the beauty is, think of these as being vectors of functions. So if I do the vectors of functions, then what I have are the product in each position, then added up. So remember that the product of the first 2 positions plus the product of the second 2 and so on. Well, if I carry it all the way through, it beautifully turns out to be exactly this version, okay? Essentially looking just like the product of this, sorry, this is a dot product there. This is still a dot. So u dotted with dv dt produces a scalar. V dotted with du dt produces a scalar. And this would be a good one for you to prove on your own. I would probably just make it a 2-dimensional or even at most a 3-dimensional vector. Okay. And it's actually a very, very simple proof. But there is a version of the product rule. The question is there a version of the quotient rule? No, because there's no such thing as a quotient involving vectors in any form whatsoever. Doesn't matter whether, if there's scalar or vectors, there's no quotients. So that's the last of those particular rules. Now, what can we do with some of these rules? Well, let me go back to something we did last week. When we did the projection, we established projection, there was something that I did, and I didn't really go through it heavily. But if I said, consider vector u being u1, u2, dot, 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 un. See, when we do vector rules, the vector rules we do have to be true always, not true only in specific instances. There is only one vector rule that is dimension specific. That's cross product, because it's only defined in 3 dimensions. Every other vector rule that exists has to be true in every dimension, or it's not true at all. There are no exceptions to that. So therefore, whenever we talk about rules of vectors, we usually just generically say vectors in n dimensions. Okay. So if I said, what is u dotted with u? You'd say, well, if I dot u with itself, that's going to be u1 squared, u2 squared, plus all the way down to un squared. But I noticed something very important about that. Because if I had said, what's the length of vector u, then isn't the length of u the square root of u1 squared plus u2 squared all the way down to un squared? Well, that's the definition of the length. Therefore, u dot u is equal to the square of the length. And that's a really nice feature. Again, a vector dotted with itself is equal to the square of its magnitude. That's kind of an important concept there, and it can be extremely useful. Now, one of the things you notice that I don't use IJK notation in vectors. I was fortunate that of the million math and upper level courses I've had in my life, I have never once had an instructor ever use IJ or K. And there's a lot of reasons. One, it has no meaning whatsoever outside of 3 dimensions. There's no analogy in higher dimensions. And when you work with vectors, you're generally working with n dimensions. But secondly, in every conceivable capacity mathematically, this has exactly one meaning. This does not mean vector in any context. I means the square root of -1 in every conceivable scenario, and all vectors are allowed to have imaginary numbers in them. So you can't have I be a double meaning. Secondly, the very fact that when people use vector notation, I means 1, 0, or I means 1, 0, 0. This is the only area in all of mathematics where somebody gives 2 completely unrelated in every conceivable way meanings to the exact same symbol. You see, this is ambiguous. Is it 2 dimensions or is it 3? Well, therefore, never use it because it's ambiguous. Yikes. But mostly because I always means square root of -1. And if you're an engineer, J means square root of -1. And in calculus, K means curvature, which is actually a really popular thing that we're going to do next day. IJ and K and others means something else in every vector context. So I tend to avoid them like the plague in a vector scenario. So I've got this situation here. Now let's suppose, suppose I have a vector R of t, call it. Suppose the length of vector R of t is constant. Now, that means I have a vector with constant length. So that vector probably isn't a vector of functions necessarily, although it could be. It could have sines and cosines, for example. But it's a vector of constant length. All right, we're going to do some examples of that today. But if I have a vector of constant length, no matter what the value of t is, I want to show a really cool result of this. This is true. Now let's start off with what is R of t then dotted with R of t? Well, I know that's c squared. I know that. Okay, that comes from right there. Then what is the derivative of R of t dotted with R of t? Well, we just established the product rule a moment ago. So that would be the first times dotted with, excuse me, the derivative of the second. Now, the reason that I can say second dotted with the first is because dot product is commutative. Cross product is not, but dot product is. So it's totally okay then to write m the second, well, of course, that is R of t, dotted with the first. And this result would be then 2 R of t's dotted with dr dt. Great. So what's the point of that? Well, that would be true anytime I ask you to do the derivative of a vector dotted with itself. It's always going to equal this quantity, except that r dot r, we started by saying that's a constant. So the derivative of r dot r is also equal to the derivative of c squared. So although this statement here is always true no matter what the original r is, if this statement is true, then this statement must equal 0. Ooh. So that means that r dotted with its derivative must be 0. Well, the only way a dot product between 2 vectors can be 0 is if the vectors are orthogonal. And that is a very powerful conclusion. In English, whenever you have a vector of constant length, it is orthogonal to its derivative. And that can be very, very useful. That's not an automatic thing. In fact, in general, vectors are not orthogonal to their derivatives, period. In general, that is not true. It was only true if I started with a vector of constant length. So we want to consider a couple scenarios where this might be the case. So I'm going to start with some 2-dimensional stuff just because it's easier to analyze, and then we'll move into 3D. Remember, we don't do n-dimensional results in general in this class. That's only a formula thing. For those in Math 254, linear algebra, you only do n dimensions. You never specifically do 2 or 3 dimensions. In fact, 3 is the only one we probably never do. Right? Let's consider a circle. In fact, let's make it simple. Let's consider a circle of radius r. So I've got x squared plus y squared equals, in fact, let me not use r. Let's say a squared. I'm saving r for something else. I have a circle of radius a centered at the origin. What I would like to do is use a vector valued function to describe this circle. So how am I going to do that? Well, I'm going to have to be a little bit clever. So if I'm at the point right here, call this point x comma y, I want xy to actually be the terminal point of this vector right here. So as I move around the circle, I want to be able to describe each point on the circle as the terminal point of a vector. Well, I can't do that with two variables. I need to parameterize this into one variable. So this is what you did at the end of Calc 2, is that you did parameterizations. So in this case here, we'd say, let's let x of t be a cosine t and y of t be a sine t. So if I do a quick check, okay, then the x comma y would be exactly this point, right? A cos comma a sine. We know that would be true. And then a quick check, also x squared plus y squared would be a squared cos squared plus a squared sine squared, which in fact equals a squared. So this particular parameterization would be perfect for this circle. So we will now define our position vector r of t as being a cos t, a sine t, okay? So that particular vector will allow us every point on the circle. So if t is 0, for example, I'd be at a cos 0, which is a sine 0, which is 0, and I'd be at this point right here. If t is pi over 2, I'd be here, and so on. So this makes it nice. So let's suppose this is how you're moving around the circle, and you can use t as time. T is the angle, but I think of t as time. So at 2 pi, a time of 2 pi, I'm back to here. A time of 4 pi, I'm back to here, and so on. I would like to now describe motion in general. So starting with this, in general, we know that dr dt is the vector of derivatives. Okay, if r of t is a vector of functions, then dr dt is a vector of derivatives. But I want you to think about the units. If r is measured as being a position, then these are length units. Then what is the magnitude of r? The magnitude of r would involve length. Now remember, magnitude has units. Some of you are still confusing magnitude and absolute value. They actually have nothing in common. They are so far from being the same thing. Absolute value only applies to complex numbers on the complex number plane. It's how far something is from 0 on the complex plane. And if you have no imaginary numbers, it's just how far from 0 on the number line. That's it. In other words, absolute value is very specifically one-dimensional. Absolute value has no units. You said, but it's distance. Yeah, but it's distance on a unitless scale. Magnitude has to have units. Magnitude isn't length. Magnitude is whatever you're measuring. So if you're measuring length, then your magnitude is length. But what if you're measuring area? What if you're measuring force? Oh yeah, force is a vector. Its magnitude must be in force units. So magnitude has to do with the length of a vector and given units. So what is dr dt? Well, it's the rate of change of a length per time. Rate of change of length per time. That's a distance per time thing. Turns out this is the definition of what we call v of t, or velocity. The derivative of position is what we call the velocity vector. Now, velocity is not speed. They are often confused. And the problem is, before we get to Calc 3, we use the terms interchangeably, but they're not exactly the same thing. You see, if I said, I want you to go in a general that way direction, and I want you to drive 100 miles an hour. Well, your speed is obviously 100 miles an hour. 100 miles an hour is directionless. Oh, 100 miles an hour in that direction now makes it a vector. Velocity is speed in a direction. So right off the bat, we'll make this very clear. The length of the velocity vector is defined to be speed. Speed does not have a direction. Speed is a magnitude. And what are the units of speed? Distance per time. Again, magnitude of a vector has to have units. So in this case, that would be our units. So if v of t is velocity, then let's go back to our circle. I'm moving around the circle. Then v of t, which is dr dt, would equal negative a sine t, a cos t. Now, what does that vector look like? This is the vector r of t. Now, that vector right there points in a different direction. And by the way, we can do a really quick check here. If I do the dot product of these two, I'd have negative a squared cosine plus a squared cosine, and that is in fact 0. The dot product between r of t and its derivative was 0 because why? The length of r of t is constant. The length of r of t, if I calculate it, is just a. It's just the radius of the circle. So what does this vector look like on my circle here? Well, if cos comma sine puts me in the first quadrant, then negative sine comma cos puts me in the second at exactly a right angle. So where this one was r of t, this is v of t. But if I'm moving around the circle, I'm at this point. Remember, we always orient a vector at the origin when we're describing its components. But if I'm out in the real world, the vector can start right here. The vector can start over here. It doesn't have to start at the origin. It's starting and then it's going in a certain direction, a certain distance. So if I pick this vector up and I place it at the endpoint, which is actually where it should be, right? This vector here, oh, notice as I'm moving around the circle, that vector would be, well, we've already determined they're at right angles. And we know that for a radial segment, there's exactly one tangent line. That vector is tangent to the circle at the place this hits. Interesting. So my position vector and my velocity vector are orthogonal. And this one's actually tangent to the circle, which makes sense. As I'm moving around the circle, like I like to say it, when I hit the banana peel in space, you know, which way will I slide when I slip? So as I'm moving around the circle and I get to this point, I would slide in that direction. If I got to this point, I would slide in that direction. You will always slide in a direction that is tangent to the surface, or in this case, to the curve of where I am. So we can clearly see that that's at a right angle. And this is nice, it works like this. So if the derivative of my position vector is velocity, I don't need this piece anymore, then what about the second derivative of my position vector, which we actually use formal notation, and that would be dv dt. That turns out to be the definition of the acceleration vector. Now think about the units, the instantaneous rate of change of velocity with respect to time. So your units would be acceleration units, right? They would be length per time squared. But this vector right here is called the acceleration vector. Now, using this particular example right here, what would our acceleration vector be? Here. Which in this case, I write it's dv dt, a negative a cos t, negative a sine t. Now, do you notice something? It's exactly the negative of my r of t. So my acceleration vector can actually be there if I orient it from the origin. So as I'm moving around the circle and I'm at this point right here, that's my position vector, that's my velocity, but my acceleration vector, if I pick it up, would actually, from this position, point right back to the center. Well, that's kind of interesting. It's actually the negative of my position. So as I move around the circle, my acceleration vector, no matter where I am on my circle, my acceleration vector will always point right back to the origin. Isn't that interesting? I wonder why. Okay. Now, if you've ever taken chemistry, all right, and you put all your little vials of stuff and you put it in that little spinny thing called a centrifuge, and you spin it around really fast and it causes them to separate and you get all this kind of stuff. right? You get the precipitate on top and get the other stuff on the bottom. This is used with blood all the time to separate the plasma and things like that. That's called a centrifuge. And as I'm spinning it around, which way is the force and which way is the acceleration? This is a very interesting concept because this is what we're going to look at right here. As I'm moving, my position is always pointing outwards from the center. My velocity is always tangent to the circle, and my acceleration is always pointed right straight back in. There's two different effects going on here. Now, you know, one of Newton's laws is for every action, there's an equal and opposite reaction. I don't like that wording because a reaction is a physical thing. So I like using different wording. I like to say for every action, there is an action in the opposite direction. To say an opposite action seems kind of ambiguous, okay? An action in the opposite direction. So wherever the force is going, there will be a force in the opposite direction. Wherever the acceleration is going, there will be something accelerating in the opposite direction. I remember when I was a kid, going to Knott's Berry Farm as a kid, okay? That's like near Disneyland. And I remember it was probably the most evil thing ever created. There was this room you went in, it was a circular room, and you stood there and the room started spinning. And it started spinning faster and faster and faster. And I remember I'm a little kid and there's this big, huge fat guy standing next to me. Okay. The reason I noticed that is as the room starts spinning, I look and the floor was gone. So we're all pinned against the wall as this thing's spinning around and I'm not falling, but neither is the fat guy next to me. Now, I'm probably 50 pounds, he's probably 300 pounds, and both of us are being held up as we're spinning around. Now, as the spinning starts getting slower and slower, the floor came back, and then we eventually were able to walk out. Of course, I was dizzy for the next 3 days. It was terrible. But what is the physical phenomenon that just took place? It's this. We were in a centrifuge, and what was pinning us against the wall is called centrifugal force. The force of the centrifuge is pushing outwards. But as we were spinning around, which way was our acceleration? Our acceleration was always towards the center. The force acting on us was pointed straight out at us, but our acceleration of movement was pointed straight in. So then one of the questions that I think is awesome is, at what point did the floor leave? And why didn't it matter how heavy the guy next to me was? Because we were both experiencing the exact same acceleration due to gravity. So at what point does the floor drop out? When the acceleration of the centrifuge is equal to the acceleration of gravity. So the force pushing us against would be equal to the force pushing us down, and it's kind of a stalemate. It's kind of a cool and interesting effect, but we can describe it with this vector right here. So now, am I moving in? No. Now, we say there's two different things taking place here. Now, there's a lot of ways you can think about this. You know, when I'm hitting the punching bag, I'm depositing energy into the punching bag, but my arm is also absorbing all sorts of energy. It doesn't feel so good. The energy from movement, where I'm hitting the bag, right? What's the study of movement called? Kinesiology. Kinesthetic movement, in this case, that's called kinetic energy. The energy that the bag is taking on and storing, if you want to think of it that way, or depositing back into my arm is called the potential energy. When the water is moving in the stream and there's a dam, and then the water, you know, from the dam is turning the turbines, right, and creating electricity, that's the potential energy that is stored, caused from the movement, the kinetic energy of the water. Those are the equal amounts of energy, because energy is a scalar. Energy is a result of a dot product, remember. But the forces, okay, remember, equal and opposite reaction, that's where all of that stuff figures in. Now, that's less important for us, but we have to understand direction. So acceleration this way, I'm being pushed out, but my motion's actually towards the center at all times. Interesting concept. So again, the concept of a centrifuge, I'm moving on a circle. So it's very easy to show this mathematically. Now, just in general, if I'm in 3D, and I have a position vector that describes where I am at any given time, then describing the velocity and the acceleration should actually be trivial. So let's do a simple example of that. Suppose I have a position vector that says at any time t, I am 3t squared cos t e to the 2t. That's where I am at any time t. All right. So if I ask you, where am I at time 0, for example? At time 0, I'd be 0, 1, 1. That's where I would be in space. So from the origin, I would create that vector, and that's where I would be in space. So here's what I'd like to know. Let's find v of t and a of t at, how about t equal pi? Let's keep it simple. I want v of t and I want a of t at t equal pi. Well, that means I have to find v of t and I have to find a of t. And one of the things I always have to remind people, you don't evaluate, then take your derivatives, because then all your answers will be 0. Always take your derivatives, then evaluate, because otherwise you get a little bit of trouble there. So first thing I'm going to do is find v of t. That is the vector of derivatives. So that would be 6t negative sine t 2 times e to the 2t. Next, we'll find a of t. Again, the hat indicates these are vectors, not scalar valued functions. And then the derivative across would be 6 negative cos 4 e to the 2t. These are my two vectors in general for all values of t. So what are they at specifically t equals pi? Now, by the way, don't say v of t equals, say v of pi equals. That'd be 6 pi. The sine of pi is 0. 2 times e to the 2 pi. Okay. Here, I'd have a of pi. That would be 6 positive 1 4e to the 2 pi. Now, there's nothing about my answer that's particularly interesting. It was just the how-to. So I take the derivative of each of the individual components to find the velocity, and then I take those derivatives to find acceleration, and then I'm probably going to evaluate. It is rare that an answer to a question is in terms of a vector of functions. More often than not, you're going to find your derivatives, and then you're going to evaluate them, and the answer to the question you're seeking will be that exactly. So if I said exactly how fast am I going when t is pi, how fast am I going? That's not a speed, that's a vector. So how fast are you going at t equal pi? Well, let's answer that one. So if I wanted speed at t equal pi, then the first thing I need to do is find the magnitude. No, I don't have to find the magnitude of v of t. I can just straight up find the magnitude of this guy. So that's going to be the square of 6 pi plus the square of 0 plus the square of this, which would be 4e to the 4 pi, all under the root. So that's my answer. Now, generally speaking, that would have units. So there would be some units distance per time, but I would have had to know those units before I started the problem. So in this case, I'm not going to put units because I wasn't given any. I know if you're sitting in a physics class, they would want you to write things like units after the answer, even though you don't have any yet. All right. So what we've been looking at so far is supposed to be pretty simple stuff. There's really nothing about this that should throw you or tremendously challenge you. So the next thing I want to do is a really, really simple example of how to describe motion in 3 dimensions in a really simple case. So motion in general can be described with r of t, but more often than not, that would have to be given to you. Can I ever figure it out on my own? Yes, I can in the next scenario. So we're going to do a very artificial scenario. And what I mean by that is, if I threw an object up in the air and wait for it to come down, I know forces of gravity are acting on it, but so are other things like air resistance. I have things like that. I have different frictions. And we have to be really careful because there's a tendency that we take Newton's laws at face value. We don't actually think about them. See, one of Newton's laws is that all things fall at the same rate. Do they really? In fact, I'm going to take 2 things right now. I'm going to take 2 things. I have 2 pieces of paper. These 2 pieces of paper are not only exactly the same in every conceivable way, they're the same. They're the same mass. They're the same everything. So if I drop these pieces of paper from the Empire State Building, right, they should take exactly the same amount of time to hit the ground. So I know when I drop these two pieces of paper, they should fall at exactly the same rate. No, they didn't. The wadded up one fell at about 10 times the rate of the other one. So does that mean Newton was lying to us? Well, that's not Newton's law. Newton's law isn't that all things fall in the same rate or fall at the same rate. Newton's law is that all things in a vacuum fall at the same rate. And last time I checked, none of us live in a vacuum. So in other words, that law is never true ever, unless the objects have the same mass and the same surface area. And if you didn't learn that one in physics, you probably should have. No, objects do not fall at the same rate. Hence a parachute. See, when you jump out of the plane, why is it that the parachute slows you down? You've increased the mass, but what you did was you have this huge surface area. And so what happens is there's something called air resistance. Oh, okay, so when the surface area is so big, there's actually a force going in the other direction that slows me down. And then it'll slow me down until I completely stop up in the air. No. It just slows you down so you don't hit the ground quite so fast. You're still going to be moving because there's still gravity. There's just greater surface area. So the artificial conditions we're going to discuss here are that we're going to assume a couple things. We're going to assume that the object, we're going to throw an object or shoot it up in the air, is not so big that we have to worry about surface area. In other words, something small. And secondly, it's not going so fast that we have to worry about something called terminal velocity, which I always love, because terminal velocity makes it sound like you're stopping. You know, it's the old Bugs Bunny. Remember, the plane is about to hit the ground, and there's two different versions of Bugs Bunny. Right before it hits the ground, it stops because he ran out of gas. That's one of them. And the other one, right before it hits the ground, it stops because he hit terminal velocity, which means you stop. No, it's not terminal velocity at all. That's a horrible term. Terminal velocity means you're going so fast that the air resistance is now the acceleration due to your air resistance is now equal to the acceleration due to gravity, and you will no longer speed up. And for the remaining time, you're going to fall at a constant rate. It's not terminal velocity, it's terminal acceleration. Your acceleration is now zero because you're moving at a constant speed. You're going really fast. We're going to assume that our object is not going so fast we have to worry about terminal velocity. So in other words, we're going to play catch in a vacuum. Okay, very artificial, but it allows us to model things a certain way. So if you guys remember going all the way back to baby algebra and even in calculus, right? If we wanted to play catch, we had to stand in the same spot and I had to throw the object straight up in the air and wait for it to come down. So it would always start with an object is thrown straight up into the air at a certain initial speed, maybe from a certain height off the ground. When will it reach its highest point? How long will it take to reach its highest point? When will it hit the ground? And the one question you didn't answer was how fast was it going when it hit the ground? You didn't usually do that one, but you did all those others. But it only was true if we stood in the same spot and I threw vertically. Or I'm up in an airplane and I throw a rock down. Well, I don't want to have to play on a line. I want to be able to have you stand across the room and I'm going to throw the football to you. I'm going to throw the ball to you. I'm going to throw my wadded up piece of paper to you. Now, we are in 3 dimensions, but motion in this case is not 3-dimensional. Motion in this case is 2-dimensional. Because you and I, when we're playing catch, all of the motion will be on the same plane. Now, think about that. Okay, we're not on the same line. There's a line between us on the floor, but think of a wall, 2 dimensions. So wherever my partner is, when I throw the ball to them and they throw it to me, the ball is moving on a curve, but that curve stays on the same plane. Now, if there's a strong gust of wind blowing sideways, yeah, that changes things. We're going to rule that out. Right? We're in a very perfect environment. We're in a vacuum. So when I throw the ball to you, the only thing affecting the motion should be gravity. That's the only thing. Now, a lot of folks get confused on the whole gravity issue. So I'm on a cliff here, okay? And hopefully I'm not too close to the cliff. And I throw a ball. Now, I might throw the ball up. I might throw the ball sideways. The question is, and let's say this is really, really long. This is Grand Canyon. And I throw the ball this way. I throw it perfectly horizontal. Well, obviously the ball's going to drop. Does gravity affect the horizontal? That's a tough one. Anybody want to chime in? Just yell it. Does gravity affect the horizontal? Nope. No, most people mistakenly say yes. No, gravity only affects the vertical. So when does it hit the ground? Well, it hits the ground. And by the way, if I drop the thing, it's still going to hit the ground. But if I throw it, it's going to continue going sideways at the same speed, believe it or not, until it hits the ground. So it's going to, the farther I am up in the air, the longer it's going to travel. But gravity only affects the vertical. What affects the horizontal? The speed with which it leaves my hand. Now, assuming I don't hit a bird, there's not a strong wind, it's going to continue moving in a constant speed horizontally, but it's going to continue building up speed vertically because of gravity. So that's one of the things that's different. Again, in Calc 1, even Calc 2, we played vertically, now we're going to play across. So what we want to be able to do is describe the motion. There's only two things that work here. There's an X and a Y. I don't have a third component. In other words, I said between me and the person I'm playing catch with, we live on the same plane. Yes, we're in 3D, but our plane is going straight up and down. You see, I have a wall here. Let's suppose I rotate my wall this way, and now it's going across the room. That's still a wall. The wall is two-dimensional. Even though I'm in 3D, that wall is two-dimensional. And if I stay on that wall, I'm staying on the same plane at all times. That's what's happening when you're throwing the ball. So think of it like this. There's the Y, there's the X. And let's assume you're off the ground. Now, most of the textbooks just butcher this hopelessly. They'll say, okay, you're going to throw a ball or whatever from a height of 0. You realize how hard it would be to throw from a height of 0? That means, first of all, I'd have to dig a hole probably around 6 to 7 feet deep. And then when I throw the ball, my hand must be exactly at ground level when I let go of the ball. That's really hard to do. See, if I'm standing upright on the ground and I let go of the ball, it's not leaving from a height of 0. It's probably leaving from a height of at least 6 feet. Oh, so you don't start from a height of 0. That's unrealistic and it's darn near impossible. Okay, so I throw the ball and it's going to go like that. Now we're going to assume there's no motor, there's no jetpack. I'm throwing an object. Maybe I have a catapult. Maybe I have a one of those crossbows. I launch it with some tremendous speed, but it's still being launched and then it's on its own. Gravity is the only thing at that point. So there's no motor to keep it up in the air. We're making that assumption. Now, if I look at that picture, it's going to hit the ground over here. Okay, so I'm going to figure it. So when I say how far away it lands, we're talking about that horizontal distance. If I say how high did it reach, we're talking about that vertical height. How long is it in the air? How fast is it going when it hits the ground? So at this point right here, let me draw a horizontal and a vertical. Here's my initial speed. It would be tangent to the motion. And you notice my initial speed is going to have some X and it's going to have some Y in the direction. That's really, really important. Now, in baby algebra, here's what you did. This is the universal. This is going back to, I'm talking about remedial algebra. If we call S of t your position, and this is what we did back then, we said time, distance traveled. And that's why it always looked like a parabola, because even though I'm throwing it straight up and down, 1 second later, this is how high I am. 2 seconds later, this is how high I am. 3 seconds later, this is how high. I was plotting versus time. That's why it gave the illusion that it's traveling. No, it's going straight up and down, okay? And the equation that we always used, up here, is this is negative 1/2 g t squared plus v0 t plus s0. That's the universal equation, where g is gravity, and we as just a scalar, not a sign. So I put the negative in front, so I have a negative value. Okay, so if I was using metric, we'd usually use about 9.8. If we were doing English standard, we usually use about 32. By the way, both of those are hugely rounded. It's not 32 exactly, and it's not 9.8 exactly, but at a convenience. And so that's the formula we always used way back when. So when we were doing English standard, for example, 32 feet per second squared, then you had something that looked like this. And if you think back, you go, oh yeah, they always started with a negative 16. Why is that? Because it was that. Okay. Now V0, initial speed. How fast is it going when it left your hand or left the, the catapult? S0, initial height. How high off the ground was I when I started? Now, that was when I was only moving vertically. We have to change it slightly. Now, this equation here gave rise to, then what would the derivative of this be? Negative gt plus v0, and then what would the acceleration be? Just negative g. Oh, that makes perfect sense, because the only thing acting on the object was gravity, right? Again, no motor. This is what we did when it was vertical motion. So everything about this is going to be exactly the same, except that can't quite be right. Because if I said, all right, I'm throwing it at 100 miles an hour, well, is it 100 miles an hour straight up, 100 miles an hour straight across, 100 miles an hour at an angle? Oh, I'm now throwing it at an angle. So I need to describe how much of that's in the vertical, how much of that's in the horizontal. It's a SOHCAHTOA kind of thing. So that's where this is going to change slightly. So let me erase some of this. So let's start with our horizontal motion. That's the easier of the two. So if V0 is our initial speed when it leaves, let's just say I'm throwing the object. When it leaves my hand, it's leaving it at a speed of V0, and I'm S0 above the ground. Whether I'm using metric or English standard isn't important at that point. So x of t, what is x of t? Well, what is my initial speed? It's V0. Oh, but wait a minute, that angle right there, let's call that angle theta. The angle made with the horizontal. By the way, if theta were 90 degrees, then it's going straight up and down. It's not moving horizontally at all. If theta is 0, then it's going horizontally, but it's also going to hit the ground really fast. So if I was trying to throw the ball at a distance, I really need the angle to be more than 0 degrees, obviously. So what is this? This is V0 cos theta t. This would be a scalar. V0 cos theta is exactly how much of this is in the x direction. How much of this speed is in the x direction is V0 cos theta. And we said there's nothing affecting it, so it's just going to go sideways forever. What is y of t? Well, that's the equation we just had a moment ago, right? Negative 1/2 gt squared plus, but not V0 exactly. Now, how much of it is in the vertical direction? That would be V0 sine of theta t. That's the only difference between what we did in baby algebra and what we're doing now, is we're not going straight up and down anymore, plus S0. Okay? So this is the universal governing formulas. So my R of t is x of t, y of t. Now, from there, I can ask things like, okay, when will it reach its highest point? How far away will it hit the ground? How fast is it going when it hits the ground? We'll be able to answer all those questions. Again, I said it's artificial in that we're ignoring air resistance and terminal velocity and things like that. We're playing catch in a vacuum, which is not very realistic, but it's a start. It's how we can model. You see, it becomes a little more complicated if I start throwing in things like, well, what if we throw in a parachute? And yeah, what if we do? Okay, in physics, maybe you'll throw in those things. But for now, we're going to keep it simple. So let's do a really simple example of this. All right, you're standing, let's say, on a cliff way up high in the air. You're on a cliff. Here's the ocean down below. And let's say you are 768 feet in the air. Now I'm going to use feet for one simple reason. When you do the problem with feet and 32 feet per second squared, it's a lot easier to get happy numbers, right? If you're going to do metric and you're going to do 9.81 meters per second, oh yes, everything's going to be icky. Okay. Everything's going to be really icky. So I am up here and I'm going to throw something, or I'm going to launch, however you want to say it. Okay. A projectile, probably a rock. A projectile is launched 768 feet above the ocean. With an initial speed, let's say of 128 feet per second at an angle of 30 degrees. Now, you could use radians. There's nothing wrong with that, but the radians aren't going to be part of your answer. You're going to be taking the sine and cosine of the angle. So it might be easier to just use simple English, okay? Because it's not 30 degrees in my calculation, it's the sine and cosine. So it doesn't really matter if my angle's in radians or in degrees. Now, when I describe this motion, that means I launched it like that, an angle of 30 degrees. Now it's going to go like this. So there's a few things we want to do. First of all, let's describe the motion. That means I'm going to need to find an R of t. Okay. When will it hit the ground? Or I'm sorry, hit the water. How's that? Sorry. When will it hit the water? How far away? Will it hit? Now, when we say how far away, we're always talking about the horizontal distance. If you were trying to calculate the arc length, then you're making an egregious error. You're going to fly from here to New York, and let's say that's 3,000 miles. That's probably not. Let's say it's 3,000 miles. Well, aren't you going to go up in the air, several miles up in the air, and then you're going to come back down? So if you track the arc length, maybe you flew 5,000 miles. I don't know, but we say New York's 3,000 miles away. So how far did you fly? We only use the horizontal distance on the ground when we talk about how far away something is. We do not talk about the arc length. Be careful with that, because then if I said I'm going to throw an object straight up in the air, it went way up in the air and it came right back down. How far away did it land? 5 miles. Yeah, but it landed exactly in the same spot I threw it. Oh, because I was tracking the arc length rather than the horizontal. Yeah, you would only track the horizontal distance. So don't make it hard on yourself. So how far away it lands is that distance. It's not the length of the arc. That's not the same. Okay, you'd actually have to say how far was the arc that it traveled on. Okay, plot its course that it traveled in that sense. And finally, how fast when it hits the water. When it hits the water. I was going to say the H2O, but we'll just say the water. All right, I may not have enough room for all of these. I may have to erase something. So the first thing we have to do is describe the vector. So I need the x of t and I need the y of t. So x of t is, okay, well, my speed is 128. My angle is 30 degrees. So x of t is 128 cosine 30 degrees. Oops, sorry. Can't read my own writing here. Cosine 30 degrees t. Well, the cosine of 30 degrees is root 3 over 2. So this would be 64 root 3 t. Now, some of you just can't help yourselves and you want to give me a decimal value for this. That would be an egregious error. There's an absolute that has never changed in the history of the world in all math science contexts. Under no situation do you ever approximate a coefficient. You can approximate a final answer. You cannot approximate a coefficient. If I was graphing a line and my slope was 1/3, I use 1/3. I don't use a decimal approximation of 1/3 because then every y value would be wrong. I plug in my x values, do a calculation, and if it's necessary to give a decimal for the answer, that's fine. But you never approximate the numbers you use to do your calculation, especially when you have a calculator. Now, what is that? I don't want to know what 64 times root 3 is, because what if my t was a root 3? Then my answer would be an integer and you've got an icky decimal in place of it. No, you don't do that. That's just crazy talk. All right, y of t. What's y of t? Well, we're using English standard, so we're going to use 32 feet per second squared, just because it makes it easier. So then that would mean that this is negative 16 t squared plus 128 sine of 30 degrees times t plus 768. And you notice this is in feet because this is feet per second squared times second squared. This is feet per second times second, and this is feet. So when all said and done, this looks like it's going to be negative 16t squared. Sine of 30 is just a half. So that'd be plus 64t plus 768. Yeah. So I'll write it up high now. I think I'm going to erase this now. I'm not going to be able to fit all this. So the first question was basically describe the motion. R of t is the vector 64 root 3 t comma negative 16t squared plus 64t plus 768. Now I can describe the motion. So if t is time, then you can tell me where you are at every second, at least until you hit the ground. You see, if you give me a ridiculously large value of t, you're going to get a really large negative y. Nah, you hit the water and you're done. Okay. Second, when will it hit the water? Well, when's it going to hit the water? It's going to hit the water when y is 0. So for part 2, for the second question, find t so that y of t equals 0. So that's just algebra. That's simple algebra. So what I want to do is set this equation right here equal to 0. So let's do that. So a little room here. Don't want to mess with my picture. That's really important. So I've got negative 16t squared plus 64t plus 768, and I want to set that equal to 0. And of course, I can use my quadratic formula. And then I can notice that all those numbers are multiples of 16. So if I get out my handy dandy calculator, if I factor out a negative 16, I get t squared minus 4t. Now, how many times does 16 go into 768? I believe that's 48 times. Let me check. 768 divided by 16 is, yep. So that would be minus 48. Let's see, did I do that correctly? Make sure my algebra is good here. Okay, now what do I do with that? Well, I set that equal to 0. And then I really only have to solve that piece right there. I'm going to have smaller numbers. All right. I'm going to erase this stuff now. This is the problem having a small board. Okay, so the next thing is I need to set that equal to 0. That would be a little bit easier now. So using my quadratic formula. Now in real life, so when I ask this question, I tend to give you really happy numbers. Okay, I give you really happy numbers and everything comes out integer values. And you know, in reality, it's probably not going to be the case. Irrational probably is more logical. So use my quadratic formula, 4 plus or minus the square root of b squared minus 4 times 1 times negative 48. So it'd be plus 192 all over 2. Well, that's root 208. Does root 208 reduce? Well, let's see. 208, I think, does 16 go into 208? I think it does. So root 208, this would be 4 plus or minus 4 root 13 over 2. Not as bad as I thought. So that's 2 plus or minus 2 root 13. Now we're finding time. We're finding the time it's going to take to hit the water. Time can't be negative. 2 minus 2 root 13 is negative. So the time has to be 2 plus 2 root 13. So the time is 2 plus 2 root 13 seconds. That's how long it's going to take to hit the water. And what do I want to do with that? I'm asking you first of all, when it hits the ground or when it hits the water is this. The next question is how far away will it hit? I'm going to plug that into that. Then I'll know how far away it hits. I got to erase this now. I think I have everything I need up there. So how far away will it hit? will be x of 2 plus 2 root 13, which would be 64 root 3 times 2 plus 2 root 13. Now, obviously, that's a hideous answer. And by the way, it is absolutely correct for me to multiply this out. This is absolutely correct. If I wrote this 128 root 39 feet, this is absolutely correct. So later on today, when you go down to Home Depot and you're going to buy some lumber and you say, okay, I need 128 root 3 plus 128 root 39 feet of wood, they're going to look at you like you're completely insane. This is when you pull out your calculator and give a decimal approximation. Yeah, that's exactly the answer. I haven't the slightest idea of the size, the magnitude of that. Is that even a big number? I don't know. So use your calculator. 128 root 3 plus 128 root 39 is approximately 1,021.06 feet. Now, how many decimals you go is not really that important. In fact, the 0.06 is probably kind of meaningless. I'm going to land over 1,000 feet away. That's what's important. Whoa. Now, the last piece of the puzzle. How fast are you going? There's some common sense at work here. You started 768 feet off the ground. Now, again, we're saying we're ignoring air resistance. So think of this. I start this high off the ground. I'm going to go up in the air. At some point, I'm coming down. I'm going to be at the exact same height. Then I should be going exactly the same speed. Now, remember, this is going to go way up in the air. And as it comes down, when it hits 768 feet above the ground, I should be going at the same speed. And then it has another 768 feet to fall. Meaning when it hits the water, it should be going faster than the initial speed. Okay, has to be going faster. A bad answer would be, well, besides a negative number, you're finding magnitude of a vector, you really can't get negative. 0 would be a bad answer, but an answer that was slower than my initial speed would be a bad answer. That means I actually slowed down on the way down. Probably not going to happen. So the last piece is I need the speed. So I'll write it out. The last piece, how fast are we going when we hit the water? Is I want V of 2 plus 2 root 13, and I want its magnitude. That's the speed on impact. So the speed on impact is always the speed of the time that it took you to actually hit the ground, or in this case, hit the water. So, well, let's see, I need a V of t. I don't actually have that yet. So I go back to the original problem and I take the derivative of my r of t. So V of t is, this is a linear function, so it's just 64 root 3, negative 32t plus 64, that's V of t. V of 2 plus 2 root 13. Well, you notice this isn't going to change. Oh, so Mr. Brown said your horizontal speed is never going to change. Well, we just showed it's never going to change. It's a constant. But this will. So when I multiply, let's do this off to the side. Negative 32 times 2 plus 2 root 13 plus 64. That would be negative 64 negative 64 root 13 plus 64. Oh, it was canceled. So this will be negative 64 root 13. Notice the horizontal speed is constant. So forevermore it's moving in that direction at a constant speed. Notice the vertical is negative. That's because I'm going down. I'm going down really, really fast. So the answer to the question that we're looking for is, what is the magnitude of this vector? So the magnitude, the speed on impact, is 64 root 3 squared plus negative 64 root 13 squared under the square root. And by the way, the number under the root is in fact an integer. I should not have a decimal under my root. My final answer is going to be a decimal, but that's not. Okay, so 64 Now, here's something kind of interesting. This is why you don't do decimals along the way. It's exactly 256. That's kind of cool. It's exact. This is an integer answer, even though my time was irrational. My answer is an integer. But if I had been doing decimals along the way, this would be off. This is feet per second. Now, does that answer make sense? Well, my initial speed was 128 feet per second, but I was way off the ground. So by the time it hit the ground, the speed had doubled. That is reasonable. Is there unreasonable? Well, slower. You know, if I said, well, I left at 128, in other words, I'm throwing the thing as hard as I can. I'm not shooting it out of a rocket. If you said it's going about, a million miles an hour when it hits the ground, it's probably a little bit fast compared to my initial speed. It's hard to know a bad answer, but if they're extremely different, if my initial speed and my impact speed are way too far apart, that may indicate that, yeah, something might have gone wrong. But it's kind of an interesting problem, and it's certainly not complicated. Again, we've overly simplified it by making the rules just, no wind, no birds hitting it, but it gives us a nice, interesting model to set up the problem. Okay, so we're going to stop now.